Feel
Okay, hi everyone. Sorry about that. So welcome. Thank you for joining tonight. I'll make this about an hour for your review session today. You feel free to ask me any questions you may have for your exam, either Thursday or Friday. As a reminder, if you're in Dr. Bengali's class, your exam is in class at 11:15, 11:10, whatever time class starts, 11:10 to 12:25, and you'll just take it in class. It'll be all multiple choice, and there's a seating chart that he put out today. If you're in Dr. Altamos's class, you'll either have it at 1:50 or 3 p.m. on Friday. Yours is multiple choice and short answer. Also, again, take it in class, also a seating chart. Just make sure you look at that before you show up to your respective test. I think that's all the announcements. And then, so we'll do this tonight. This will be recorded and posted if you want to watch it back. And then tomorrow I will also have my review session from 5:30 to like 7-ish, and Heldenfels 111. So that's what I have in terms of review materials and announcements. With that, I'll open the chat to questions. You can I pulled up the mock exams. You can literally ask me anything. This hour is yours. Yep. So someone asked me when my review session is. It's at 5:30 in room 111 in Heldenfels. Okay, and then someone is asking for a theoretical and actual yield, and so we can do that first. Okay, so when we talk about theoretical versus actual, right, just make sure that you know the difference. Theoretical is something you would get like from a limiting reagent question. And then your actual is something that you would like collect in lab. Okay, so your theoretical is what you expect to get, your actual is what you actually collect. So okay, so we'll do this one. So we have 10 grams of C2H6 or ethane react with 10 grams of oxygen. If 8 grams of CO2 is collected, what is the percent yield? For this question, the first thing you want to know is that you want to set up your reaction first, right? So you have C2H6 and O2, and what kind of reaction is this? Yep, this is a combustion reaction. So we have CO2 and H2O produced, right? That'll always be what's happening with combustion reactions. What's the next thing we need to do?
Balance equation.
Perfect. Yep. So I'm going to put a 2 here. I'm going to put a 3 here. That makes my oxygens bad. So I'm going to put a 2 here. I'm going to put a 4 here. I'm going to put a 6 here. And I'm going to put a 5 here. Okay, so now we have a balance reaction. What's the next thing we need to do?
Convert grams of C2H6 into moles.
Yep, perfect, right? So we're next going to find the limiting reactant. Oh, it might be 7. I don't know. 8, 6, yeah, sorry. Thank you. Right, so then we need to convert our grams of our reactants into moles. We're going to find the limiting reactant. We're given information about our reactants, but not our products. We don't know, right? Our end goal is to find the percent yield. So we need an actual yield and we need a theoretical yield. So in order to find the theoretical yield, we need to find how much carbon dioxide can be produced. So we'll take 10 grams of C2H6 and we'll convert this to moles. And this is 1224, 30.06 grams. And then what ratio do we use in order to find our limiting reagent? Yep, that's, so someone said 7-2 or 2-7. That's definitely one option. You can either compare your reactants to reactants, or you compare your reactants to products. So this can diverge in two ways. You can either say that for every 2 moles of C2H6, you need 7 moles of O2. Right, or you can do that for every 2 moles of C2H6, you need 4 moles of carbon dioxide, right? You can compare reactant to reactant, or you can compare reactant to product. Either one of those works. So right, so in either case, right, you can get 1.16 moles of O2, or you can get 0.665 moles of CO2. Okay, if you're comparing your moles of O2, you then want to convert this back into grams. This is 37.12 grams. Okay, we then need to do that for our oxygen as well. I'm going to compare this to the product. Yes, I'm doing this to see what's the limiting reagent, because yes, I'm doing this to see which one is the limiting reagent. I won't further explain yet. Okay, so I compare my reactant to the same product, right? CO2. I prefer this method. You do whatever you want to do, whatever is going to get you to the correct answer. I like looking at this because I can say, okay, if I use all of my 10 grams of ethane, I'm going to produce 0.665 moles of carbon dioxide. And if I use all 10 grams of my oxygen, I'm going to produce 0.1786 moles of carbon dioxide. So I know that because I produce the least amount of carbon dioxide when I use up all of my oxygen, that has to be my limiting reagent. So I know that my limiting reagent is O2, and the most of carbon dioxide that I can collect is 0.1786. Okay, so we know that that is the number we have to move forward with. Once we know how many moles of carbon dioxide can be produced, we need to convert that into grams. And we can use that we can do that using our molar mass. And we get 7.86 grams of CO2. I would use, so on your periodic table that you're given, I would use all of the numbers that are given to you on that mass. So I think that goes out to 3 decimal places. I would use that directly or use all of those numbers when you're solving your molar mass. I just have memorized these, so I'm just doing it shorthand for right now. But on your actual exam, just make sure you use all 3 decimal points that are given, 3 or 4, whatever's given. Okay, so now that we found our limiting reagent to be oxygen and that we can produce 7.86 grams of CO2, what does that tell us? Good, this becomes our theoretical yield. Okay, this is our theoretical yield. How does that help us? What are we solving for? What's our original question? Right, we need percent yield. So our percent yield is actual over theoretical times 100. Do we have all of the information that we need in order to find our percent yield? Yep, now we do. So what goes in for our actual? Yep. We collected 8, and then our actual, or then our theoretical was what we just found, which is 7.86. And what do we get for a percent yield? Right, we get about 102. Yep, perfect. Yeah, about 102% yield. So a chat or a question did come in. Usually the actual yield is going to be smaller than your theoretical yield. I just made up numbers, so I didn't really know what was going on here. Or I didn't know what to expect. But sometimes you do get over 100% yield. This could be due to imperfections or right, sometimes you have to dry something, it's not fully dry, so it weighs heavier than it's supposed to. There are a lot of factors that might contribute to a over 100% yield, but most of the time it's going to be less than 100%. But for the sake of this problem, right, we're just looking for an answer, so that works. But in this case, our percent yield's 102, and that would be that. Does that help clear up some actual and theoretical? Awesome. Okay, let me see what else was asked. Okay, someone asked for a titration problem. Okay, so when we do titration, remember this is always going to be an acid and base reaction. Your acid will have an H and your base will most likely have an OH minus. Okay. So Okay. Sorry, this is like kind of poorly written, but sometimes I start a sentence and I don't know where it's going. All right, so for this one, we're saying what concentration of H2SO4 is required to completely titrate 38.5 milliliters of 0.555 molar lithium hydroxide if 25 mils of H2SO4 was used, right? So we're saying that 25 mils of H2SO4 was used to completely titrate 38.5 mils of lithium hydroxide. So we don't know what concentration of H2SO4 was used for this. And I don't think any or other practice exams exist besides what was given to you. But I will put together, I'm working on putting together some more practice problems based off of the practice exam. So I would just recommend looking on the internet for further practice problems besides your mock exams. Okay, so for this question, and for titration questions in general, I highly recommend writing out the chemical reaction for what's happening. So we have H2SO4 and we have lithium hydroxide. Which one here is our acid and which one here is our base?
H2SO4 is the acid and LiOH is the base.
Perfect. Okay, so H2SO4 is an acid and lithium hydroxide is a base. These two are both in the chart of strong acids and strong bases, and so those I would highly recommend memorizing. They're the 6 strong acids and 6 strong bases are just required for you to memorize. You're going to be using them a lot. Okay. What gets produced from a titration reaction? You do not get the strong acids and strong bases on an exam. Yep. H2O is going to be produced, and what's your other product? Yep, it's going to be an ionic compound. It's going to be a salt. It's going to be lithium 2SO4. What do we need to do once we've written out our chemical reaction? Good, we need to balance. How are we going to do that? Yep, so lithium is always going to be a +1 and the sulfate ion is always a -2. So you need 2 lithium ions to balance out the charge from the sulfate. And lithium is in group 1, so that will always hold the +1. And then sulfate is a polyatomic ion that you'll be given. So you can check the chart for that charge, but that one does have a -2 charge. Yep, and we're going to use coefficients. So we have to put a 2 here and then a 2 here. And I think that does it. Perfect. Okay, and then we're given milliliters and we're given molarity of lithium hydroxide. What can we get from milliliters and concentration? Good, we can get moles. So 38.5 mils, we do need to change into liters. So this is going to be 0.0385 liters. And then anytime you see the capital M, that's molarity. What's our units in capital M? M equals, good, moles over liters. Remember, this is liters of solution. So we can use that molarity and we can say that we have 0.555 moles over 1 liter. So we have a total of oops. Right, we have 0.0214 moles of lithium hydroxide. One reason that I really like to write out the balanced equation is that then you can see your ratio between acid and base. So do we have a 1-to-1 acid to base ratio here? No, we do not have a 1-to-1 ratio. What is our ratio? Good, it's 1-to-2 acid to base. And we knew which milliliter to use first because we are completely titrating 38.5 milliliters of that concentrated lithium hydroxide. And we used 25.0 milliliters of H2SO4 to completely titrate it. It's poorly worded. It will make more sense on the exam. I'm just coming this off the dome. So apologies if that was confusing, but we're using 38.5 milliliters of lithium hydroxide, which is why those go together. So we have 0.0214 moles of lithium hydroxide. And we have a 1-to-2 acid to base ratio. So for every 2 moles lithium hydroxide, we only need 1 mole of H2SO4. So this means that we only need 0.0107 moles of sulfuric acid. Once we have our moles of H2SO4, what can we use in order to find concentration? Good, now this is where we can use our 25 mils. Can we use it directly as 25 milliliters? Nope, we cannot use it directly as 25 milliliters. So we can take 0.0107 moles divided by 0.025 liters. And I get about 0.427 molar H2SO4. Okay, any questions on titrations? If you want to check your answer, there is a version of M1V1 is equal to M2V2. It is the molarity of the acid over the volume of the acid divided by the coefficient in front of the acid is equal to the molarity of the base times the volume of the base divided by the coefficient of the base. So you can use this and check it for what we just did. In our equation, right? This 1 that's here, this is A, and this 2 here, this is B. So that's how you would plug it in. It will probably just say H2SO4. I don't think you need to, or it'll say sulfuric acid and then give you H2SO4 in parentheses. But H2SO4 is a strong acid, so I think that is something that you do need to memorize. For the exam. You just need to know that it's a strong acid. Nope, you are given your solubility chart, and I highly recommend looking at whatever mock exam you were given for whatever class you're in, and looking at the reference sheet that they provide you with the mock exam. That will be the same reference sheet that you get as well. Any other questions on titrations? Does that help with that? So do both strong and weak acids have H element? The short answer is yes. The long answer is no. Anything can be an acid. It's, but for right now, just know your 6 strong acids and those all have the H element. If it is not a strong acid, they will tell you it is a weak acid. I can go over the strong and just the strong acids and bases. So your strong acids are HCl, HBr, HI, HNO3, HClO4, and H2SO4. And your strong bases are lithium hydroxide, sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide, and barium hydroxide. Those are just the 6 you're required to know. Yep, and so if it's not one of these 6 strong acids or strong bases, then you can consider it weak. Yep. Reactions with weak acids and bases just means it will not completely dissociate. So that's something like acetic acid. All right, this is one you might see a lot. This does not completely dissociate. So here we see the H element, that H at the very end, shows that it is a acid, but it is a weak acid. So in solution, this stays as a whole compound. It does not dissociate, right? This is a covalent compound. It'll not break apart into ions in solution. So this would be a non-electrolyte because it's not dissolving and not creating ions. Non-electrolytes, right? Electrolytes are produced by different ions in your solution, right? Sodium and chloride are pretty big electrolytes that you need in your body. Potassium is another one. Right? So ionic compounds create electrolytes. Strong acids and strong bases create electrolytes. Anything else is a non-electrolyte. Or I'm sorry, anything that does not dissociate is a non-electrolyte. Yeah, I believe the question will tell you if it's a weak compound. I don't know if it'll necessarily tell you it is a strong compound. And that'll then determine the question, right? It might just be a titration question and it'll just ask for acids and bases, and so it doesn't really matter. If they're asking an electrolyte compound, they probably won't tell you if it's strong or weak. You'll have to know that. Yeah, as long as you know your 6 strong acids, 6 strong bases, most of them are going to be strong. Most of the time they use a strong acid and a strong base in like your in your titration questions. ClO4, I believe is on the polyatomic ion. It might not be actually. I don't know if ClO4 is on the polyatomic ion, but they don't use that one very often. It really only shows up with perchloric acid. So a weak electrolyte and a non-electrolyte. So some things are slightly dissolvable. So things that are technically a weak acid will be weak electrolytes. So if you say if the question says this is a weak electrolyte or this is a weak acid, what kind of electrolyte is it? Then it'll be a weak electrolyte because some things will partially dissolve. A non-electrolyte would be something that does not dissolve at all, right? So it just stays at a singular compound. So something like oxygen, right? Double bonded oxygen dissolved in water will not dissolve. This would be O2 is a non-electrolyte. Right, it just stays as that oxygen compound. Or CH, right, does not dissolve. That just stays as a CH or like ethane, C2H6, right, is not going to dissolve and break apart into ions. It'll just stay as this compound, and so that's a non-electrolyte. But something like acetic acid, the CH3COOH, is a weak acid, which means it partially dissociates. So there are some H plus ions in solution and some CH3COO minus ions, right? Like a little bit of H plus in CH3COO minus. And so that means it's a weak electrolyte. So this plays into like net ionic equations. So if you had something like right, something like this. This does not, in your net ionic equation, when you split this up, this first acetic acid does not dissociate. So for your complete ionic equation, right, you have CH3COOH, you have lithium and hydroxide, you have H2O, and this now becomes an ionic compound. So this is lithium and CH3COO minus. The only thing that you can now cancel out is the lithium ions. So your net ionic equation keeps that first compound and everything else. And the only thing that we really care about is the water and the ion at the very end. So hopefully that answered that one question that I saw pop in. Okay, I have a couple questions on molecular speed, so we'll do that. Anything else on net ionic equations before I move on from that? I think most of the net ionic equations I've seen have been like a precipitate question, so don't hang yourself too much on, or don't get hung up too much on weak acids and whatnot here. Focus more on solubility and predicting products for solubility and writing net ionic equations for that. So this would all be aqueous. This would be liquid, and this is aqueous for that one. So Mason, if it's not on your solubility chart and it is not one of your 6 strong acids or 6 strong bases, you can assume that it has to stay as its compound. Right, if you recognize that it is an acid and it's not one of the 6 strong acids, you can assume that it has to stay as its full compound and it's not going to dissociate in the net ionic equation. Definitely double check the solubility chart just to make sure that that ion's not on there, but if it's not on the solubility chart and it's not one of the 6 strong acids, 6 strong bases, just keep it together. Insoluble will not dissociate, right? Correct. So that'll stay as its compound. It's not going to break up into its ions. Yep. Alrighty. We'll do a little bit of kinetic molecular theory. So when we talk about diffusion / effusion, right? These are different. And diffusion is what we usually talk about most. We have 2 equations. We have rate 2 over rate 1 is equal to the square root of molecular weight 1 over molecular or molar mass 2. Right, the thing to point out here is that it goes 2, 1, 1, 2 as you go across your reaction, right? So these match up here and these match up here. This one is given to you on your formula sheet. It's not something you need to memorize. So just double check your reference sheet if you get confused. He personally did not tell me if diffusion or effusion will be on the test, but it is on the mock exam and it is a part of chapter 5. So I would assume that it is fair game to be asked about on your exam. Okay, so the big thing between this one is that your heavier gas will move slower, right? And your lighter gas is going to move faster. So whatever one, right? If you have a lighter gas, it'll effuse faster out of a balloon or faster out of a container, whatever it's in, than your slower gas. You can find the molar mass, right? So this molar mass comes from the periodic table. So if you get a molar mass of like 32, that's most likely going to be oxygen, right? Because that's a diatomic element. So if you find or you're looking for something, maybe it's fluorine gas, right? Or something like that. So you can always look at your periodic table to identify what gas that is because you're solving for the molecular weight or the molar mass, and that comes from the periodic table. So you can say okay, so oxygen diffuses out of a container at a rate of 1.35 meters per second. What rate does chlorine gas diffuse out of the container? So for this problem, we are going to use rate 2 over rate 1 is equal to the square root of molar mass 1 over molar mass 2. This is a paper exam, so feel free to write all over your exam. Oxygen is what we're going to be looking at first, so I'm going to call this molar mass 1. And this is the first rate I'm given, and it's 4 oxygens. This is going to be rate 1. Chlorine gas is my second thing that I'm given, so this will be molar mass 2. So I'm looking for rate 2. So I have X over 1.35 meters per second. What's the molar mass of oxygen? $32. Yep. So, yep, it's 32 because oxygen is diatomic, right? You have 7 diatomic molecules: nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, and then hydrogen. Okay, so you do want to remember those 7 are all diatomic. What is the molar mass for chlorine gas? Perfect. And so before you even plug this into your calculator, what are we expecting the rate of the chlorine gas to be? Should it be greater than 1.35 or less than 1.35? It should be less than, right? We just said that your heavier molar mass will move slower. So the rate at which chlorine will effuse out of this container is going to be slower than the oxygen molecules, because the oxygen particles are moving faster and they're able to escape faster. So then we get X is equal to 0.672 meters per second. Does that match our prediction? Yes, it does, right? This is smaller than 1.35. We could say, does this make sense? We can say, yes, this makes sense, right? Chlorine's going to be moving slower. So that would be our answer there. The unit is meters per second because that's what was given in our question, right? We're given meters per second here from our original rate, and so that will stick with us. The rate units can change. It can be kilometers per hour. It can be centimeters per second. That doesn't matter. Rate can be changing. I think. Oh, did I forget to do that? I did forget to do that. Sorry. I'm not done yet. Okay, sorry. This is 0.9. Yep. Okay. Sorry. Thank you, Juliana. Yep. So this would be 0.907. This is still smaller than 1.35. So that isolates X. I missed a step. Apologies. It still matches our prediction. So just make sure you finish your algebra. Okay. We have probably time for like one or two more questions. And if I don't get to your question today, right, we do have more time tomorrow. I'll answer as much as I can in the next 2 days. Okay. I have a couple questions for solution stoichiometry. Excuse me. When we talk about solution stoichiometry, I want you to refer back to like this titration question. They're going to be very similar questions between titrations and then solution stoichiometry. You will most likely have something with a volume and a molarity that you need to get to moles to, and then, right, you're combining some things together. So you just want to pay attention to the volume, and you want to pay attention to if you're producing a product, if you're producing a precipitate, something like that. But once you get to moles, then you're able to convert between products and reactants very easily, so you can find how much precipitate is forming, or like what your limiting reagent is, something like that. You're able to do that once you get your molarity and your liters, combine those to get to moles. So that's my stick there for solution stoichiometry. We can focus on that a little bit more tomorrow. I have an abundance question. So for VRMS, that's going to be very similar to what we just did. This is a derivative of VRMS if you're looking at both, if you're comparing to effusion rates. That's really the question they're going to ask, I think. I don't really think they're going to have you use VRMS by itself. If you do need to use VRMS by itself, that is given to you on your reference sheet. So just make sure you reference that equation for that one. And then, yes. And then someone's asking about where my practice problems are going to be. Those are on the office hours page for either class. It's either under the office hours tab if you're in Dr. Altamos's, or it's under the resources tab if you're in Dr. Bengali's. You just have to scroll down a little bit once you get to both of those pages, and then everything should be there. I'll also make an announcement with that as well. Okay. The answers for both mock exams are posted now. I think they were posted earlier today for both classes. Okay, and then I also saw something for non-ideal gases. I'm not going to focus too much on that today. The thing to know with non-ideal gases is that they start to behave non-ideally at lower temperatures and at high pressures. So at ideal conditions are high temperatures and low pressures. So just make sure that that's really what you need to know for non-ideal gases. Yep, and then last week's practice problem set that I've created has already been posted with the answers. Or I guess like last week would be the practice questions I'm making for the exam. So that'll be posted by tomorrow at the very latest, or by tomorrow night at the very latest. I was trying to see what questions y'all had first before I like focused on any of those. Okay. I guess that's a good time. We'll get back to that. So if you're on Canvas, if you're in Dr. Altamos's classes, on the home page, if you go to office hours, which is right this button in the middle, office hours, and then you scroll down a little bit, I have my Chem 107 IA sessions. Those are all of those. The extra practice problems and the answers will be what I post for the practice exam. So that's that class. If you are in Dr. Bengali's class, this resources and contacts page in the center. Right, I'm your IA, here's a link to all review session resources, and that's there. That's that. Okay. Is there something burning we want to do in the last 5 minutes? Okay. So for percent abundance, this is usually going to be a chart. So this has to deal with your isotopes. There are not any other mock exams or past exams for you to take. It's just what's given, the single exam given by each professor. So percent abundance deals with isotopes. The value on the periodic table, the molar mass or molecular weight for that element, is the result of all of the weighted averages of the isotopes known for that element. So a lot of the times they use like gallium, right? I feel like we get a lot of those. Or if we look at carbon, there's carbon 12, there's carbon 13, and there's carbon 14, right? So these are the 3 isotopes that exist for carbon. I forget what oxygen is, but I think oxygen is 15 and oxygen 16, something like that. Oxygen 7, I don't know. Right, but if you have these 2 isotopes, then you would be given the isotope as a chart, and it'd be oxygen 15 and oxygen 16. You'd be given the mass and AMU, and this would be 14.999, and this would be 16.111. And then you would give your percent abundance. If you're given 1% abundance, then you can find the other one. If you're given neither, then you can say that this would be X and this is 1 minus X. And then you can solve for X that way for each respective percent abundance for each of those masses. So if we're trying to find the percent abundance of oxygen for both of these, right? We can take our molar mass from the periodic table for oxygen, which I think is given to you as 15.996, something like that. I think on your periodic table. And you set this up by saying the mass times its percent abundance plus the other mass times its percent abundance. And then you can solve for X in both of these cases. Right, so we would get X is 10.3%. Yep, X would always be less than 1 here. They have to add up to 1, but your X value would be less than 1. So your percent abundance for isotope 15 is 10%, and then that means that your isotope for oxygen 16 is 90%. Right, and that would make sense because the molar mass for oxygen is closer to 16 than it is to 15. And so we need a lot more of that 16 isotope to bring up the average of that molar mass compared to the 14 or the 15. Okay, does that help my percent abundance questions? I did put that one on some extra practice problems, and I'd have a couple of those from later or from earlier in the semester too. And that's, I think, when you're solving for both percent abundances, that's the hardest. That is the hardest question here, is to find both the percent abundances. Percent abundance usually equals 100%. Maybe it'll be like 99.99, but for the most part, it'll equal 100%. Yep, you could have a problem with 3 different isotopes. At that point, they're usually trying to solve for one of the masses of the isotopes. So you should be able to solve for all 3% abundances of them given the question. And then you're just adding another variable to your percent abundance. So right, it's like, or percent abundance, excuse me, to your average atomic mass. So that would be, right, if we talked about, what did I just say, carbon 12, it would be 12 times its percent abundance, 99%, 98%. And then let's say we don't know carbon 13s, right? So that would be X times 1%. And then we would have 14 times 1%, right? You're just adding another variable there. But you would just be plugging in an X value for that mass that you don't know. Okay. I think this seems like a good place to stop for the evening. If you have any additional questions or if there's some extra practice problems you would like to see, please feel free to email me. I'll make a couple of them to include with the document that I'm making right now. And other than that, I'll see you tomorrow. No. Other than that, if you do have any questions, like burning questions of, I really don't understand this topic, feel free to email me before my review session tomorrow, or feel free to bring a question to my review session tomorrow. Email Dr. Bengali or Dr. Altimos. And yeah, I would just say keep practicing. If you're going through the mock exam, if you're making mistakes, just make sure you understand why you're making those mistakes. Go back and look at your old quizzes, go back and look at your old homeworks, and just make sure you get familiar with the chemistry language. And I think that will be super helpful. Yep, and then my review tomorrow is at Heldenfels 111 at 5:30. Hopefully this was helpful. Thank you for coming. And this will be recorded and posted. Yeah, I think the mock exam is a pretty good representation of what the exam will be like. Yep. So not to say that you got 100 on the mock exam, you're going to get 100 on the test, but very similar topics, I think, will be asked. So that's good. Thank y'all. Have a great night. I'll get this posted as soon as possible. Good luck.